two things I want to point out before I start. The first one is that I'm Nicholas, the second author of this paper, and the first author, Philip. He worked on this during his bachelor thesis with us. We turned that into this paper for now. So from my side, quick congratulations again for his nice work. And the second point is that I might get a bit detailed during this presentation. So whenever I want to make an emphasis on something which might not be so technical, I'm going to include the symbol over here to catch up with everyone. Why this symbol? Simply because it's the last talk before lunch and I needed some symbol. So what did we try to do? We tried to evade HTTP censorship using HTTP request smuggling. And for that, let's take a quick look just to get everyone on the same page how HTTP censorship looks like. Well, usually we do have some kind of client that wants to connect to some kind of server, which usually is a website, and there is a censor in between. And if the censor, if the client now sends a message to the server, that is usually intercepted by the censor, and if the censor decides to block this message, it somehow tears down the connection. And I don't want to focus too much on how it tears down this connection. Instead, I want to focus on, if we go back one step, how does the censor decide whether to block this connection or not, specifically for the HTTP case. And for that, let's take a look at this exemplary HTTP message. It has all the parts you get HTTP request might have. But what's important for a censor is first the request path, which indicates the actual resource that the client might want to access, in this case index.html. And secondly, it includes the host header that indicates not the specific path, but the website overall. In this case, it's censor.org, so that might just be a website a censor might want to block, leading to censorship behavior from the censor. And what we, and I guess many of us here, are interested in is not necessarily, or also how does the censor look at a request and how does it block the request, and we're also interested in how can we circumvent the censorship so that the request, which would be blocked initially, is not blocked but still understandable by the server. And what's important here is that it's easy to, or maybe not easy, but what one can do is one can just scramble a message such that it's basically unrecognizable but for the censor. But what's important is that the server still needs to understand the message, because if it doesn't, well, what did we gain in the first place, right? So just some examples from previous research is usually we try to slightly modify a request. For example, inject white spaces, line breaks, or changing the letters in the host header or somewhere else from lowercase to uppercase, vice versa, and so on. So small changes, hopefully circumventing the censor and hopefully also being accepted by the server on the other end. And what I want to focus on, or what I want to emphasize here, is that previous work focused on altering a single message. So there was a message we want to get to the server, the censor blocks it, so how can we alter this message in some way that the censor doesn't block it anymore and the server does still understand it. And what we instead do, it's similar but not quite the same, is instead of altering the original message, we thought, well, why don't we just put it inside another message which looks harmless, like a letter in two different envelopes. And if the censor only sees the outer request, then we're good to go, right? That's a bit abstract, so how does that look like? So consider the same request as before. It's the same one as above, but without any alterations. We're still trying to access censor.org. But instead of altering this message somehow, what we're doing instead is we're putting it inside another request. To be specific, we're putting it in the body of another request, whatever that means for now. And notice how the host headers of both requests are not the same. So the inner one tries to access or points to censor.org, saying, hey, I want to access censor.org, but the outer one says something like an example.com, which might not be censored. It can be exchanged by any other uncensored or even not existing domain. And what we would hope now to achieve is that from the censor's perspective, it just ignores the inner request, treats it as some request body, analyzes the headers instead, only sees example.com and forwards the message to the server. Basically, ignoring is allowing us to circumvent censorship that has been there in the first place. On the other hand, we would hope that the server instead recognizes a second request and also treats it like a second request, so that it sees the first request, sees also the second request, and answers to both, or maybe only the second if it only serves censor.org, but not example.com. That's a little bit abstract. I talked about how we're hiding one request inside another request, specifically in the body of another request, but how can we achieve that? This is where I'm going to get a bit technical, but I'm still trying to keep it simple. So HTTP has two different headers which allow us to indicate where a body starts and or ends. And the, at least in my opinion, more intuitive one is the content length header, which basically says, or in this example says, well, my body has 15 bytes, and then there are, if I counted correctly, 15 bytes in the body, request ends, we're finished. The second one is transfer encoding. It has multiple instantiations. I'm not going to focus on all of them here. Instead, I'm going to focus on the chunked instantiation because that's an alternative for content length. For chunked, what we are doing is instead of transferring our data in as one big blob, we can divide it into different chunks, hence the name of the encoding. In this case, for example, a chunk of size 9, a chunk of size 6, and then send them both. What's important here is that chunked encoding always ends with a chunk of size 0. So when the HTTP parser tries to parse the body and sees the 0, it knows, okay, right, I can stop taking a look at this request. The next request is already starting. I'm done here. And what happens now, what would happen if one might get creative and thinks, well, I could just take both headers in one request, and they could say the same, but maybe they could not. They could say, in this example, content length indicates a body of 50 bytes, which is all of the rest here, and transfer encoding says chunked, immediately ends the body, and the second request starts. So the standard says transfer encoding should come first, but what the standards say and what servers do are sometimes different things. So servers do get confused when they see these kinds of headers. And even if we have servers that say, all right, or they want to conform to the standards and say, well, of course I'm going to take transfer encoding, what happens if I, coming back to previous research, alter these headers? Servers again might get confused. One server might say, yeah, whatever, I'm going to ignore the transfer encoding header where I swapped or exchanged letters against uppercase letters and so on and so on. So it's, even for servers that try to be correct, it's still hard. And this general concept of, it's called HTTP request smuggling, this general concept has been known to the web security community for quite some time. James Kettle did a lot of work on it. These are just two examples. There has been a paper that tried to find these working alterations using automated fuzzing. There are tools on GitHub that try to find these vulnerabilities in servers. And what we now took a look at is we saw, well, this is a vulnerability that exploits mismatches between HTTP parsers in front-end and back-end servers. Can we somehow extend this to exploit mismatches between HTTP sensors and, well, front-end servers, back-end servers, basically any kind of HTTP servers we are actually trying to access? And to wrap up this transition a bit, let's take a look at how this request we just talked about, or the request we just saw, would hopefully turn out in a sensor and server setting. So the client would send a request, or a smuggled request, which has both the content length and transfer encoding header. And we would now hope that, well, the server or the sensor intercepts it, of course, and we would hope that in this case the sensor interprets the content length header, which says 50 bytes are coming, treats everything as body, ignores the second request, and forwards it to the server. And on the server side, we would hope that the server interprets the transfer encoding header, which says request immediately ending now, and then can also see the second request and also answer for the second request or answer to the second request and give us access to the censored resource we wanted to access in the first place. And this is nice in theory and all, but we not only thought, is that possible? We tried out whether that works, and the simple and for us very satisfying answer is that yes, it does work. How did we find out that it works? Well, first we took a look at some web servers. We took Apache, Nginx in different versions, and also live websites, so actual HTTP websites from the Citizen Lab list, which are censored or considered to be censored, and just try to find out which test vectors, so which alterations of content length and transfer encoding headers are accepted by these servers. So do they answer to the second request we are sending, or do they, well, never interpret it in the first place? We then took all the working alterations to 3 countries, China, Russia, and Iran. We rented a vantage point there and through all these alterations through the censors to find out, well, which of these alterations now also circumvent censors. And in the end, that left us with a bunch of techniques which are both accepted by servers and circumvent censors together. This is an excerpt from the paper. Don't worry, I'm not going to go into the details of that. But on the left side, you can see some of the techniques we tried. You might find the white spaces I talked about, some line breaks or the uppercase letters, for example. And on the top, you can see the different server versions and sensors we evaluated. As I said, we found working techniques for sensors and servers, and all I want to point out here, for the details I'm going to refer to the paper, but what I want to point out here is that depending on which server you're analyzing and which country you're analyzing, you will end up with different results. So actually taking a look at different countries makes sense, it's not the same, and also taking a look at live websites and different server versions also makes a huge difference. So this already leaves me with wrapping up this talk. I have 2 main takeaways. So the first one is that what I basically talked about for 12 minutes or something is that HTTP request smuggling does work. It does work as a censorship circumvention technique. We tried it out. We found it working on servers and sensors. And what I also want to point out is that it can be extended. So we focused on alterations on the content length header and the transfer encoding header to provoke these mismatches, but further alterations could be considered. For example, what we did is we still had the outer request to be a GET request, which had a body which is a bit weird in the HTTP setting. One could change that to POST, for example, or other requests to further confuse sensors and servers into what header or which request they want to, in the end, interpret. And the second point I want to emphasize is that what we did is we took a vulnerability from web security, HTTP request smuggling, which it has been researched. There is work on, or there was a lot of work on it. We took a look at it and basically just transferred it into a censorship circumvention technique. And what we would hope, or what we are kind of asking and hoping to find some discussion on, is the question, are there other vulnerabilities which we can similarly turn into censorship circumvention techniques without having to start all over again with finding alterations and just starting a terminal and sending random requests with a sensor? So are there other vulnerabilities we can turn into censorship circumvention techniques? I believe that completes the presentation. I'm very thankful for your attention and happy to answer questions. You're welcome.
Yeah, so we'll take some questions now.
Hi. So in 2021, the EFF said that HTTPS is truly just about everywhere. Mm-hmm. Is that correct? And if so, does that threaten the relevance of this censorship evasion technique at all?
This is a very good question. It depends. I already talked about how it makes a difference for which websites you analyze and which countries you analyze. And that also applies to where HTTPS and where HTTPS might not be so present. So if you take a look at the Citizen Lab list, for example, where these censored domains are present, the share of HTTP websites is much larger than, for example, looking at the 1,000 biggest websites on the internet. They all use HTTPS, but some censored websites still very much rely on or still offer both HTTPS and HTTP, making this still a viable circumvention technique. Still, I agree with you, looking at HTTP is not enough. HTTPS is very, very, very important.
Hi, thank you for the talk. So I had a slightly question on technical lines. So in 2018, we did a study in India where we were looking for methods to bypass the censorship. And fundamentally, I think the way you're trying to send two requests in a single connection and trying somehow that the middle box sees only the first one and processes the second one. So there is a method where you just try to end the first request using a double carriage return, and the next is automatically then treated as a separate request. So do you think something like that could also work, because it's much simpler to, so to say, implement? Like, what are your thoughts on that?
I mean, yeah, it might also work. I guess it goes into the same direction. Without thinking too much on it, I guess we can discuss it in the break maybe, but what I think is sensors might be able to fix the double line break thing a bit faster than fixing which header they try to interpret, because basically the only thing you can do to, as the only countermeasure you can have for these both headers is trying to interpret both headers, and then the sensor has to kind of take both paths and analyze both. So yeah, what you're proposing sounds like a very viable technique, so that might also be possible, yeah.
I mean, I would say that for the detection part, if there are two host headers, the fact that they only match the one, I think they're only looking for, their first match. If they look for all the host, so to say, keyword in the request, then no matter what you have in between, I think they might be able to still detect it. So, yeah.
Yeah, I mean, what we kind of focused on is that we took advantage of the fact that sensors usually only look at the headers, and whatever they consider as body, they just ignore. And yes, it will get more difficult if sensors also scan all of the body too. That's correct, yeah.
Thanks, very interesting talk. Finding these methods is a cat and mouse game, and we know sensors read pets' proceedings. Is there any fundamental advance here, or is this just more heuristics that the sensors are going to catch up to, and in 6 months we're going to be looking for more heuristics to get around them?
That's a very good point, and you are correct that this is more heuristics in the first place. That's why I'm trying to make this, or try to make the second point over here is finding these heuristics is work, and especially I think finding these heuristics from basically starting from zero is a lot of work. And without trying to downplay our own work here, what we did is we just took this vulnerability and applied it as a censorship circumvention technique. And I guess it would be, or I hope there are other vulnerabilities we can turn into these censorship circumvention techniques, trying to get some advantage in these in this cat and mouse game.
Okay, well, thank you